You can go
Yes,
for a full screen view, if in case it is possible from your side.
Full
View
screen.
full screen. You just go to
view
view, the
full screen.
third tab.
Yeah, there is a menu view
View.
Yeah, yeah,
And
full
full
then
screen.
screen.
full.
Control L.
Just a minute. Full
Control
screen.
L.
Here.
Control L.
Just come down. Yeah, yeah, yeah. Press
Control
that.
L.
How is that?
Press that.
No, but I will press
That's
control. Yeah,
perfect.
it
Perfect.
has come. It has come.
Is it okay?
Perfect.
Okay. Uh, all right. I want to talk about some result on the annihilatory graph, and in fact, also I added, maybe it's not written in the title, will be also extended zero divisory graph. Okay. As usual, R will be a commutative ring with yeah, is everything okay?
Sir.
Yes, sir.
Yes,
Yeah,
yes.
okay.
Yes.
At any time, if there is a problem, just go ahead and stop me.
Sure, sure. Please
Yeah,
go ahead.
yeah. R is a commutative ring with the non-zero uh, identity, and Z of R is the set of zero divisor of the ring. We go back to maybe early 1988 and then 1999. I put the three names together. Uh, they establish uh, zero divisory graph of a ring. What's a zero divisory graph of a ring? It's undirected symbol graph with vertices uh, uh, the zero divisor of the ring, you take away the zero. And how you connect two vertices? You connect two vertices if you multiply them and you get zero. So the vertices are the non-zero zero divisor of the ring, and two vertices are connected by an edge if and only if when you multiply them you get zero. In 2014, I introduced the annihilatory graph of R. The annihilatory graph, the same thing. The set of vertices will be the non-zero zero divisor of R. And how you connect two vertices. They are connected by an edge if and only if the annihilator of xy is not equal to the annihilator of x union the annihilator of y. And let's remember what I mean with annihilator. It's given below. If you choose an element in R, then the annihilator of M will be all the elements in R where ym equals 0. So that's the annihilator of an element in the ring R. And definitely, if it will not take you long, you realize that each edge or path of the classical zero divisor is an edge of the annihilatory graph. So it depends on how you think of it. So you can say that the zero divisory graph is going to be a subgraph of the annihilator graph. Okay. Okay, that's the introduction. Okay, and then in 2017, there are three, I think, Iranian, not I think, I know, I'm very sure they are Iranian mathematician. Uh, I have a problem pronouncing the name. I think Nikan Thierry, Nikandesh, and Nikmar introduced the extended zero divisor graph of R. What is the extended zero divisor? The same thing. It's undirected symbol graph. The vertices will be the non-zero zero divisor of the ring. And but how you connect the two vertices? Two vertices are connected by an edge if and only if the ideal generated by X intersection with the annihilator of Y is not equal 0, or the ideal generated by Y intersection with the annihilator of X is not 0. So again, the zero divisor graph definitely will be a subgraph of the extended zero divisor graph. So to follow my talk, look at the notation like this one here is the extended, where this notation here is the annihilatory graph. Okay? So I will state some result now about the annihilatory graph. If R, let R be a commutative ring and assume that the number, the cardinality of the non-zero zero divisor of R bigger or equal to 2, then the annihilatory graph is connected, and the diameter of the graph less or equal to 2. Okay, and let's stop for a minute here. We know that the diameter of the zero divisor graph is less or equal to 3. Here, the annihilatory graph, the diameter is less or equal to 2. Okay? Again, what is the annihilatory graph of a ring R? Remember, the set of vertices are the non-zero zero divisor, and two vertices are connected if and only if the annihilator of xy not equal the annihilator of x union the annihilator of y. Okay? All right. Here is another result. What about the girth? Remember, the definition of the girth is the length of the shortest cycle in the graph. So if you have a reduced ring, reduced mean the set of nilpotent element equal to 0. There is 0 is the only nilpotent element of the ring. So if R is a reduced commutative ring, and we assume that the annihilatory graph is not equal to the zero divisor graph, this notation, this is the first one, is the annihilatory graph, and assume the girth, then the conclusion, the girth is always 3. Okay, so if your ring is reduced, and I know that the annihilatory graph is different from the zero divisor graph, then I know the girth quickly. It has to be 3. Not just that, there is a cycle of length 3 in the annihilatory graph such that each edge is not an edge of the zero divisor graph. So you get some information about the ring, the structure maybe in this result. The girth is 3. Not just 3, you can construct a cycle of length 3 where each edge of the annihilatory graph of this cycle, each edge is not an edge of the zero divisor graph. Okay, here is example you can read, is an example of non-reduced commutative ring where xy is an edge of the annihilatory graph that is not an edge of the zero divisor graph. And the ring is not difficult. Take the ring to be Z8. 2, 6 is an edge of the annihilatory graph of R. Definitely. Why? How do you check that? Well, you need to check that the annihilator of 2 times 6 will be 4. The annihilator of 4 in Z8 will not be equal to the annihilator of 2 union the annihilator of 6. But definitely 2, 6 is not an edge of the zero divisor graph. Why? Because 2 times 6 is not 0. Simple. And this Z8 kind of interesting. Maybe it will appear more. Note that the annihilatory graph of R of Z8 is K3. By the way, here this is a notation. I used the Anderson notation. You know what I mean with that. This is complete graph. It's supposed to be K index by 3. But he used, exponent. Maybe there is a philosophy here. Why? Because we're talking about the graph of ring. Anyway, I'm not going to talk about philosophy here. Where the annihilatory, the zero divisor graph is K12, complete bipartite graph. The girth of the zero divisor graph for this ring is infinity. The girth for the annihilatory graph is 3. The diameter of the zero divisor graph is 2, where the diameter of the annihilator is 1. So this example kind of interesting, where you have all these different properties. The structure is different, the girth is different, diameter is different. Okay. Okay, here is the following example of a non-reduced commutative ring where the annihilator is not the same as the zero divisor, and if xy is an edge of the annihilatory graph that is not an edge of the zero divisor graph, then there is no path in the annihilator graph of length 2. Okay? And that's the example. If you take your ring to be Z2 cross Z4, you take A to be 0, 1 and B 1, 2, and C to be 0, 3. Then AB and CB, AB and CB are the only two edges of the annihilatory graph that are not edges of the zero divisor graph. Okay? But there is no path in the annihilatory graph of length 2 from A to B. And there is no path in the annihilator graph from C to B of length 2. Okay? That's interesting. All right. And here is another, okay. What about if the annihilatory graph is not the same as the zero divisory graph and the girth of the annihilator is 4? What can we say about the ring or the graph? So here is the result. Let R be a commutative ring and suppose the annihilatory graph not equal to the zero divisory graph. Then the following statements are equivalent. When you tell me the girth of the annihilatory graph is 4, definitely 1 implies 2. And remember that this result under the assumption that these two graphs are not the same. The annihilator is not the same as the zero divisor. That means if the girth is not 3, it has to be 4. I keep, I'm not sure, 4. You can read that. If xy is an edge of the annihilatory graph, that is not an edge for the zero zero divisory graph, then there is no path in the annihilatory graph of length 2 from x to y. Okay? That's kind of interesting. If you have an edge in the annihilatory graph that is not an edge, then you cannot find a path of length 2 from x to y. Okay. If these two graphs are not the same, the annihilatory graph is not the same as the zero divisory graph, then the girth has to be 3 or 4. What that mean? That mean if the annihilatory graph is not the same as the zero divisory graph, then the length of the shortest cycle in the graph has to be 3 or 4. When you think about it, it tells me more even. It tells me that I must have a cycle. If the two graphs are not the same, then we must have a cycle in the graph. Where if you study the zero divisory graph, like if you take Z8, I mean, there are many, but anyway, if you take Z8, the girth of Z8 is infinity. What I mean, by the way, girth infinity, it means there is no cycle in the graph. It means a tree. That's another way. There are many ways to say that. Okay? Okay. These three Iranian mathematicians, they said if you take any ring R, then the annihilatory graph is complete bipartite if and only if one of the following hold. The null of R is 0, and the number of the minimum prime ideal of R is 2. Null of R is not 0, and either the annihilatory graph is complete bipartite 1n, you know what that means, but you know the standard notation 1n will be down. I mean as an index, not in exponent. Or the annihilatory graph is K23, complete bipartite a graph with 5 vertices, K23. I think all of us know this structure very well. Okay, that's kind of interesting. I mean, you read a theorem, but when you stop And you think about it, it's kind of really interesting that the graph is complete bipartite, a complete answer for when is the annihilatory graph is a complete bipartite. Then it has to be reduced, because what does it mean nil of R 0? It means the ring is reduced. And not just that, the number of the minimum prime ideal of R is 2. If the ring is not reduced, then I know that the annihilatory graph has to be a tree or a star graph, or a graph with 5 vertices. Okay. Uh, I think all of you are graph theorists, so I'm not gonna, because look, we have complete bipartite graph. Like you can talk about two, or forget complete. If you remove complete, we have bipartite graph. And bipartite graph, all of us know, is different from complete bipartite graph. In bipartite graph, we only need to make sure that I can split the vertices into two sets, A and B, where every two vertices in A not connected by an edge, and every two vertices in B are not connected by an edge. You can talk about three-partite graph.
ഞാൻ പറഞ്ഞില്ലടാ മനഃപൂർവ്വം ഒച്ച ഉണ്ടാക്കുന്ന
Hello? You hear me? I hear something.
Yes, yes,
Yeah,
yes,
we
sir.
are hearing.
Okay.
Yeah, yeah.
So what do I mean with the three-partite graph? That means my set of vertices can be divided into three sets, A, B, C, where every two vertices in A not connected by an edge, every two vertices in B not connected by an edge, every two vertices in C not connected by an edge, and so on. So the Iranian mathematician, they prove this nice result. If you R is a product of integral domain, what's integral domain? Integral domain means 0 is the only zero divisor of the ring. That's integral domain. But look, they took R to be a product of integral domains where n is bigger or equal to 2. So this product, n has to be at least 2. So this is how you create zero divisor anyway. Okay, then the annihilatory graph is n choose the ceiling in over 2 partite graph. And remember what we mean m choose, this is you read it m choose n, which is m factorial of, all of you know what we mean with m choose n. Okay? So this is kind of interesting. This n is the same as how many integral domain you are taking, because look, R is d1 times d2 times, keep going till you reach dn, where n is bigger or equal to 2. Okay, so for example, I can take R to be z times z times z 3 times. So I let n to be 3. I multiply Z 3 times. Then the annihilatory graph will be 3 choose what? 3 over 2, and then you take the ceiling. So that will be 1 maybe, or 2. 2. It will be 3 choose 2. Yeah. 3 choose 2, which is what? 3. That will be a 3-partite graph. The annihilatory graph is not n choose -1. It's not gonna be 2-partite in our example. Remember, I took n to be 3. So I did z times z times z 3 times. So it will be 3-partite, but it will never be 2-partite. This is a nice result. Okay. Okay, if you have the ring is reduced, again, reduced mean 0 is the only zero divisor, 0 is the only nilpotent element of the ring R. The nil of R is 0. Let R be a reduced commutative ring that is not integral domain. Then the following are equivalent. The annihilatory graph is complete. The zero divisor graph is complete, and hence they are equal. R has to be ring isomorphic to Z2 cross Z2. That's it. So for a reduced ring, the annihilatory graph will be complete only if R is isomorphic to Z2 cross Z2. Okay, and let me remind you, like myself and maybe Anderson and others, we study graph because graph, the theory by itself is beautiful. Also give us some information about the ring. I mean, like here, there is some information about my ring. Like if the annihilatory graph is complete, then I know how my ring look like. Is nothing but Z2 cross Z2. And I know that the annihilatory graph will be the same as the zero divisor graph, right? Okay. Now, if you take a reduced commutative ring and you assume the zero divisor of R is an ideal of R. So the ring is reduced. Remember, the ring is reduced, and more than that, that the zero divisor of R is an ideal. Well, then I know quickly that the two graphs are different. The annihilatory graph is not the same as the zero divisor graph, and I know that the girth is going to be 3. Okay? Also, I mean, this is a nice result about reduced ring. Then I know, and of course here there is one condition that the 0 is an ideal. Okay. Let R be a reduced commutative ring and assume the minimum prime ideal bigger or equal to 3. Then the annihilatory graph will never be equal to the zero divisor graph, and the girth will be 3. Like if you take, reduced commutative ring, and the minimum prime ideal has to be bigger or equal to 3. For example, if you take a product of 3 field, like Z3 cross Z5 across Z7, then definitely the number of the minimum prime ideal here is what? 3. Remember, in a finite commutative ring, every prime is maximal. Of course, this is not true if the ring is infinite. There are many examples. Okay? All right. Here is, look at this result. If the ring is reduced meaning 0 is the only nilpotent element. And of course, I want my ring to be not integral domain. Then the annihilator equal to the zero divisor graph if and only if the minimum prime ideal of R equal to 2. Since in reality graphs are always finite, so like if you take Z5 cross Z7, definitely here we have the annihilatory graph equal to the zero divisor graph. Why? Because if I take Z5 cross Z7, then my ring is reduced, definitely, and the number of the minimum prime ideal is 2. Okay. Here is another thing, like for reduced ring, the following are equivalent. So again, the condition here, my ring, by the way, is it okay to ask how much time left for me?
It is technically it is 10 more minutes, but you can take a little more.
Okay.
It's interesting talk, guy.
All right, thank you. So if the ring is reduced, then the following are equivalent. The girth of the ring is 4. That tell me the girth of what? Of the annihilatory graph. Then I know the annihilatory graph is equal to the zero divisor graph, and the girth of the zero divisor graph is 4. Okay, so for a reduced commutative ring, if the girth of the annihilatory graph is 4, then I know quickly there is no difference between the zero divisor graph and the annihilatory graph. And let me remind you again, since you are here, the annihilatory graph, how you connect vertices in the annihilatory graph. Remember that two vertices, x and y, are connected by an edge. If the annihilator of xy is not equal, the annihilator of x union annihilator of y. Where in the zero divisor graph, two vertices x and y are connected by an edge if xy equals 0. I know something, if you know the girth of the annihilatory graph, then I know that the total quotient ring is isomorphic to a product of two fields. Okay? And I know how my zero divisor graph and annihilatory graph look like. They're going to be complete bipartite. So if the girth is 4 of the annihilatory graph, because we know these are the same, and then by a result by Mole and Anderson, they prove that for reduced commutative ring, the girth is 4 if and only if this is right here. But by 2, the annihilatory graph is the same as the zero divisory graph, so I come up with this for free. I only need to show that they are the same. But then this come free by a result by Molay and Anderson. Okay, what about if the girth of the annihilatory graph is infinity? Okay, then these two are the same. And that's easy because if you remember what I told you, that if the annihilatory graph is different from the zero divisory graph, then the girth has to be either 3 or 4. So so in that theorem, I have the assumption that the annihilatory graph is not equal to the zero divisory graph. Well, so I mean, 1 implies 2 will be trivial. And here is an interesting, then you know what is the total quotient as the ring structure will look like. The total quotient ring of R is isomorphic. You can say more about the minimum prime ideal and so on. Okay. For a reduced commutative ring, here is a complete answer. The annihilatory graph is equal to the zero divisory graph if and only if they have the same girth, and the girth has to be either 4 or infinity for a reduced commutative ring. Okay? So what about if the ring is not reduced and the zero divisor of R is not an ideal? Then these two are never the same, the annihilator and the zero divisory graph. Okay? You can read this if the girth is 4 for non-reduced now. Non-reduced means at least the ring have one non-trivial nilpotent element. So there are some element different from 0. Let's call it A, where A to the n is equal 0. The girth is 4. R is ring Okay, look, I mean, this is kind of things that I like. 1 and 3. As I told you, graphs are beautiful by themselves as a subject. But here, I mean, the connection between the graph and the ring structure, 1 and 3. If I know the girth of the annihilator of R is equal 4, then I know how the ring look like. It has to be this. Okay. Let me, since of the time, okay. All right. I want to take this result, kind of interesting. I mean, how, I don't know, mathematician, we are connected by spirit. There is something I define called two absorbing ideal in 2007. What is a two absorbing ideal? Whenever you, you can read it. Whenever you have 3 elements in R and the product of these 3 elements in I, then AB in I, AC in I, or BC in I. You think of two absorbing ideal as a generalization of a prime ideal. And the annihilate, look at this result. This is like a clear cut. Because look, I was studying when the annihilatory graph equal to the zero divisor graph, and I was considering cases like when the ring is reduced, and what about if the ring is not reduced? Here there is no condition. I mean, look at the result, clear cut. Also, these are Iranian mathematician. Let R be a commutative ring, then the annihilatory graph is equal to the zero divisor graph if and only if 0 is two absorbing ideal of R. This is just a beautiful, in my views, of course, beautiful is relative thing. But I was really, when I saw this result, I was said, wow, that's interesting. How they made the connection between these two graphs with the two absorbing ideal. And yeah, there is a beauty in that. And that beauty due to these people here. I did not observe that, even though I introduced the concept, but I did not observe it, that these two are the same if and only if. Okay. Okay. Let me, yeah. A work of Shelvam, Professor Shelvam, he's here, and his co-author Silva Komar. If your ring is quasi-local, then the annihilatory graph is planar if and only if. And this is also one of the, as I told you, the connection. And all of us know what planar mean. You can draw it on the floor where the edges do not cross, except at the end. I mean, at the end point, at the vertices. All of us know that from undergraduate basic graph theory, the planar thing. Look, then the annihilatory graph is planar if and only if R is isomorphic to these rings. I mean, I don't know if this is not beautiful. What does beautiful mean? You have a complete description of all rings where the annihilatory graph is planar. That's due to Shelvam and Silva Kumar. Okay. Also, they prove if R is a reduced finite ring that is not a field, and R is a product of finite field, then the annihilatory graph is planar if and only if R is isomorphic to these rings. A complete description of the rings. Also, they did it for if R is isomorphic to quasi-local finite ring with field, like combination. Like R1 can be Z8 or Z9 and so on. Z8, Z9, Z25, and you take Z3, Z5, Z7, okay? Then also, they said the annihilatory graph is planar if and only if, that's it. And again, Shelvam and Silva Komar, they did, I mean, this is a beautiful, I called this is beautiful math. You study the graph, and at the same time, you know the ring structure. I'm not exaggerating, but I think this is beautiful mathematics. Really beautiful mathematics. Yeah. Okay. Again and again, and you know, I think I will stop here. That's enough for me, and I thank you for listening. And I didn't have time to talk about the extended graph. Maybe that will be a different talk. I don't know, in the future. Thank you. I'm done.
Thank you, Professor Badavi. I think if, people here at lunchtime, but we are not ready to go for lunch. You are engrossed in your talk. So the organizers have told that you can even go for 10 more minutes in case you want to show some beautiful results.
I think I'm done. That's good enough for me.
Thank you. Thank you.
Yeah.
Thank you very much. It's, now the floor is the session is open to the floor. If someone has a question, you can type in here, or you can unmute your mic and ask directly to the professor.
I have one observation.
Yes.
Yes, sir.
Suppose R contains identity. Are the notions of two absorbing and prime are one and the same?
If R,
let me take R contains identity.
Contains
commutative ring with identity.
With identity.
Yeah. In that case, the notion of two absorbing, which is a generalization of prime, is equivalent to prime. Am I correct?
Two absorbing is two prime. What do you mean with two prime? Your definition of two prime?
No, prime.
No. If the ring is commutative with identity, you saying a prime and two absorbing are the same?
Yeah, I feel.
No.
Are they one and the same?
No, definitely no. Because
if I take C is equal to 1, what will happen?
Okay, here is, I mean, I can...
Oh, it is not for all ABC? Okay. It is not for all ABC.
Yeah, exactly.
It is for some ABC.
Yeah.
Okay,
yeah.
So, if it is for all ABC, then I can put C is equal to 1.
Oh,
AB
yeah,
implies
definitely.
AB
Yeah.
Okay, fine. Thank you.
Yeah. I mean, then, you know.
Ayman?
Yes.
Hello.
Yes.
Your talk was very nice.
Thank you very much.
I liked it. Thank you very much.
Thank you. You know the difference in time, like you said you're going to have lunch.
Yeah, 1 o'clock.
Yeah. We are like, you are ahead of me 1 hour and a half ahead of me.
Your time is just 11:30 now.
In fact, I'm sorry I was not able to attend yesterday and the day before because we started the university and I have teaching duties. In fact, I will be... Yes, in fact, I will be teaching in 20 minutes from now.
Okay. So it's time, Ayman, it is time for you to have a smoke and go for the class.
In fact, we teach online.
Oh, I see. Okay.
That's what I wanted to.
You can sit in your room
and.
In
have
fact,
you come back to normal classroom or still online?
Everything is online so far.
Online.
And I think it's the same thing in India.
No, in our state,
India, some classes have started.
Classes are partially started yesterday in physical mode. There are some standard operating